Now, waves are disturbances that propagate through some medium, or in the case of light, they're self-propagating. Those disturbances, if you have more than one, can interfere with one another. For example, if you have two waves that come together at the same time at the same place, what happens? Well, to talk about that, we have to talk about the principle of superposition and interference, when two waves interfere with one another. Superposition is just the discussion that when two disturbances, right, disturbances of waves are superimposed when they come together. So one wave says, hey, I want you to move this amount, and wave number two says, I want you to move that amount. You add those up. That is superposition. So you have to take into account the effects of all the waves at that location. And you add them all together, all the disturbances. Now, some disturbances will be positive, some disturbances will be negative, but you still add them all together. The positive and negative disturbances will cancel one another out depending on their amplitudes. Now, if the disturbances, we'll just talk about two waves interfering for a moment. If the disturbances are both positive, then we call that constructive interference. Constructive interference creates a wave with a larger amplitude than either of the individual waves. So wave number one says, I want you to move positive this amount. And wave number two says, I want you to move positive that amount too. The final wave, the disturbance is twice as big. Now, it's up to twice as big. It is twice as big if you have pure constructive interference. If you have two identical waves interfering and both of them give you the maximum, right, amplitude, then you have an amplitude that's twice as big. You have pure constructive interference. Destructive interference creates a wave with a smaller amplitude than the original waves. So you combine two waves together, but the wave you get out is actually has a smaller amplitude, therefore smaller energy than the two waves you put in. It's 0 for purely destructive interference. Destructive interference, or purely destructive interference, the wave is dead. There's no oscillations at all. Because wave number one says, I want you to move a positive X amount. Wave number two says, I want you to move a negative X amount. When you add those two things together, they equal 0. So examples drawn here. We have a red wave and a blue wave. Constructive interference is when you add the waves at each position, so you do a vertical addition. Here at the peak of this wave, we're at amplitude X. At the peak of the blue wave, at the same location, we have amplitude X. So the combined wave is twice as big, amplitude of 2x. Here we have an amplitude of minus x. Here we have an amplitude of minus x. So when you combine them, the combined amplitude is negative 2x. This is purely constructive interference. You make a stronger wave when you combine the two. Destructive interference, you can see that the blue wave now is shifted a bit by half a wavelength to the right or to the left. So when the peak amplitude occurs in wave number one, you have the strongest negative amplitude change in wave number two. Assuming those are the same height, when you add those together, you get 0. And every position along this axis, when you add these together, you end up getting 0. So you end up with purely destructive interference. Now, why would you want one or the other? Well, if you own a pair of noise-canceling headphones, you know the advantage of purely destructive interference. Noise-canceling headphones sample the sound around you, the wave around you, supply a wave that's shifted, so you get destructive interference, and the ideal is that when you listen with noise-canceling headphones, the sound outside disappears. So you have a train whistle going off nearby, the headphones cancel that out. Now they don't work perfectly. There's a time delay to sample the noise as well as produce a counter signal. But for droning sounds, things like that, ambient noise, they work pretty well. So this is pure destructive interference. This is pure constructive interference. Constructive interference just is if the wave is any bit stronger, not twice as strong, that's pure constructive, but the wave is stronger than either of the original waves, it's constructive interference. Destructive interference is when the combined wave is weaker than either of the two waves made up, then it's destructive interference. So destructive interference is also one of the reasons, if you've ever been to a concert hall, you see these large curtains on the walls and things like that. That produces a diffuse reflection of the noise, making it difficult for destructive interference to occur and you to lose part of the orchestra because of destructive interference. A weird event if you're a history buff. During the Civil War, during great battles in the Civil War, there were areas near the battlefield where observers of the battle, and the Civil War battles actually had like reporters and other people who come out to watch the battles. There were areas near the battles where there was no sound, or very little sound, even though you could see cannons going off. And further away in other areas, they could hear the battle clearly. Because of the geometry of the land and echoes and things like that, what ended up happening was you ended up getting destructive interference. And even though these powerful cannons were going off, when the cannon noise combined with its echo, or the echoes combined, you end up getting destructive interference and very little could be heard. These were called acoustic shadows during the Civil War. A couple other unique types of waves. We talked about interference, constructive and destructive interference. If you have a wave trapped on a string, for example, a guitar string, which is pinched at both ends, and you send a vibration through it, the wave hits the fixed end, travels down the string, hits the fixed end of the string, reflects and comes back through the string, hits the other fixed end, is reflected and comes back. So the wave interferes with itself. When that happens, the wave interfering with itself, you get what's called a standing wave. Now, a standing wave is a wave that appears not to move. Instead, they vibrate in place. So there'll be areas called nodes along the string where you won't see any motion. So looking at what would be normally a fixed guitar string, you'd see areas like this where you have fixed points called these nodes that don't appear to vibrate, and then the string itself will vibrate in these antinodes, the places between nodes. Go up, down, up, down, up, down. So you don't see the wave moving, you don't see the disturbance moving along the string, you just see the string, parts of the string vibrating up and down, and then other parts not moving. That's a standing wave. Any type of a stringed instrument, pluck it, you can see a standing wave. It works best for the long wavelength notes, the lower notes. Now, antinodes are just the points between the nodes that have the maximum movement. So the antinodes would be areas of maximum movement or maximum amplitude, maximum displacement between the nodes. Every instrument, stringed instrument, woodwind or whatever, has what's called a fundamental frequency. That's the lowest frequency for a guitar that can fit on that vibrating string. So you have some string, attached to a guitar. There's a fundamental frequency when you vibrate. So the note is controlled by a couple of things. It's controlled by the wavelength, but also the speed of the wave on that string. So different strings, different thicknesses of strings give you different notes. That's why on a guitar, or how the string is under tension, by changing the tension on a string, you can change its note. However, the fundamental frequency is the lowest frequency you can get on a particular vibrating string. You can't go lower than that. However, you can go higher. You can have higher frequency notes on that string. Those higher frequencies are called overtones or harmonics. And it's the combining of this fundamental frequency along with the higher harmonics that give instruments their unique sounds. For instance, if you play middle C on a piano and you play that same note on a violin, you'll note that even though it's the same frequency, you can tell which one is the violin and which one is the piano, even though both of them are vibrating strings at the same frequency, because each has a unique overtone or harmonic associated higher frequencies that give it its unique sound. Now, synthesizers or electronic keyboards that can synthesize cellos and violins and oboes and things like that. Sound engineers know what these fundamental frequencies are. They know what the overtones are for each instrument that gives its instrument its character, and can replicate that on these synthetic, at least in part, on these synthetic synthesizers, electronic synthesizers. If you've ever wondered, when you talk to someone on the telephone, especially landlines, they sound slightly different than they do when you talk to them face to face. Telephones, in order to save space and bandwidth early on, would actually cut off the higher harmonics, the higher frequencies of a person's voice, in order to save data as they transmitted the data across phone lines. So you would sound slightly different because of that. Now, there are some programs, there are some companies that advertise HD sound quality. That's just basically advertising, hey, we don't cut off the higher harmonics. You'll sound on our phone call like you sound in real life. Another thing, again, for those of you who've played a musical instrument, especially a stringed instrument, had learned in the past, is the concept of beats. Now, a beat in physics is when you have two waves of similar but not the same frequency overlap. So let's say 400 hertz or 440A, 440 hertz and 441 hertz. When those two waves overlap, they interfere. Because they're not the exact same frequency, they change between becoming constructively interfering and then destructively interfering, and then constructively interfering and destructively interfering. And what you get is a wavering note, a wow, 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 wow note that fluctuates at a frequency called the beat frequency. That beat frequency is just the difference in the two frequencies of the note. So for my example, 440 hertz and 441 hertz would have a 1 hertz difference, therefore a beat frequency of 1 hertz you'd hear in that note. Now, you can take advantage of that if you have a good ear when you're tuning like a guitar. Normally when you tune a guitar, you tune one note, tune the low note, and then the higher notes you can actually tune off of that previous note. But how do you know when the two notes are the same? You listen for the beat frequency. A rapid beat frequency means the frequencies are quite a bit different. You continue to tune it until that beat frequency, that pulsation, gets longer and longer, and then eventually when it disappears, when it's 0, you know the two frequencies are the same. So that's beat frequency, and I will link in the online tools. I should be able to find an old web page I used to like that allowed you to demonstrate on your computer picking two frequencies, combining them, and hearing the beat frequency.